Hello, welcome back to the methodology course at HEMA. We will move on now to discuss a couple of models that were not even feasible for econometricians of 10 years ago. That the power of the computers has made logit and probit models very common. But when would we want to use those models and why? Let's take a look. From this discussion, I hope that you will bring away a sense of when we should use these rather sophisticated models rather than ordinary least squares. And second, how can we interpret our coefficient estimates in logit and probit? So why bother with probit at all? Well, all of us assumes that the variable that we are trying to predict is continuous and real. For example, your weight is a continuous variable in the sense that we can express it as precisely as we wish with a real variable, 130 pounds, 130.5, and so on. However, sometimes we don't want a, a, a very precise quantitative variable. Instead, all that we want to do is to predict, for example, whether a person will smoke or not smoke, or graduate from high school or not graduate. In these cases, the dependent variable, that is the variable on the left-hand side of the equation, may not take on continuous real values, but instead only the values of 0 or 1. 1 may indicate a respondent that smokes, and 0 may indicate that the respondent does not smoke. So this is qualitative information rather than quantitative. One easy way of accommodating our need for qualitative variables is with the linear probability function. So let's suppose in this example that we set the dependent variable equal to 1 if the student has gotten an A in the business program and equal to 0 otherwise. In this case, although each observation has a value of the dependent variable of only 0 or 1, the average value across all the observations of the dependent variable gives us an idea of the probability that a typical student will get an A in business. So, for example, if we have observations of 500 students and 100 of them have received A's, then the mean of the dependent variable is 100 divided by 500, or 20%. That 20% is the probability of an A. Also, in this very simple linear probability function, the coefficients of the explanatory variables gives us sensible information. So, for example, we can determine the impact of gender on the chances for an A. And here is an example using data from the United States in 1994, a model of smoking at that time. This is from Pebble. In this case, we will set the dependent variable equal to 1 if the respondent smokes and 0 otherwise. We will add an explanatory variable for educational attainment, that is, the number of years of education completed by the respondent. And then finally, we have an independent variable that indicates whether or not the respondent is female. Set the dummy equal to 1 for females and equal to 0 for males. And here is the model of a linear probability function that results. Here are some questions for you to try. First, from the model, can you indicate the impact of another year of education by the respondent on the probability of smoking? Second, what is the probability of smoking for a male with no education? And then finally, what is the probability of smoking for a female who has completed 10 years of education? I will give you a minute to attempt those questions. Okay, time's up. Let's see how you did with the questions. So for our first question, you wish to calculate the impact of education on the probability of smoking for a typical respondent. In this case, because the coefficient of education is negative 0.029, the probability of smoking falls by 2.9% with each additional year of education. Second, what is the probability of smoking for a male with, with no education? Well, remember that we set the gender variable G equal to 0 for a male, so this will fall out. Also, the term that depends on education will also fall out because we are setting E equal to 0. So all that remains on the right hand side is the intercept. In this case, the intercept is 0.661. So the probability of smoking for the male with no education is surprisingly high, over 56%. And then finally, we want the probability of smoking for a female with 10 years of education. So in this case, we said G equal to 1 and E equal to 10. Overall, our calculation is the intercept 0.661 minus 0.29 of 10 times the coefficient on education, and then finally the gender term adds a 4 of 1,000 to our probability of smoking. Overall, the probability of smoking for this educated female is 37.5%. It's interesting to see that gender does not have nearly as much of an impact on smoking as education does. But in any event, you can see how easily we can interpret the linear probability function. Since that function is so easy to estimate and interpret it, why don't we always use it rather than more complicated alternatives? let's see, in ordinary least squares, the dependent variable in the classical case may vary from negative infinity to positive infinity. It can take on any value. However, we are interested in probabilities, not a continuous and unbounded real variable. Any probability is bounded by 0 and 1. So we have the problem that all LS may predict probabilities that are simply impossible because it permits the dependent variable to rise above 1 or to fall below 0. And here is an example of such a misleading model for linear probability functions. This also is a model from Fred Pepple, and we will now treat as the dependent variable an indication of whether the respondent belongs to an environmental group, such as Friends of the Earth. As before, we will use E to measure the number of years of education completed. And as before, we will interpret G as an indication of gender. If the respondent is female, set G equal to 1. And there is a new linear probability function. Question for you to answer in this case: what is the probability that a man with no education would belong to an environmental group? I will give you a minute to consider the answer. Are you ready? Well, let's see how you did with the model. G equals 0 and E equals 0 as well. So both of these terms drop out of the equation, and the predicted probability that the man belongs to an environmental group is negative 0.024. In other words, minus 2.4%. But this is impossible since the minimum probability is always 0, cannot be negative. So in general, the, we did get invalid estimates from a linear probability function because the dependent variable is not bounded by 0 and 1. There are other problems as well with that linear function. Any linear regression um, in the normal case has a constant coefficient on the independent variable. So, for example, we found in the first sloping model that every additional year of education will decrease the probability of smoking by almost 3%. But this is counterintuitive because we would assume that as the probability approaches either one of its bounds, that further changes become smaller and smaller. That is, we have a nonlinear relationship between the right-hand side variable and the left-hand side variable. So here's an example that considers the relationship between household income and the probability of buying a home. So let's consider what may happen in two extreme cases. First, suppose that we have zero income. Then an increase of $10,000 will not raise our probability of buying a home in particular, because even with $10,000, we cannot afford to buy the home. At the other extreme, in the case of a millionaire, another $10,000 will not affect her decisions because it is essentially pocket change. as far as she is concerned. They can already afford to buy the home with the $10 million that we already have. Now, here is a median prospect. Our household has an annual income of $100,000. Now, it may well be the case that another $10,000 may be significant at the margin, but this is the money may enable us to buy the home. So we could not have afforded it had the income of only $100,000 rather than $110,000. To sum it up, it is most likely that the relationship between income and the probability of purchasing a home is non-linear, or as its name would suggest, the linear probability function assumes a linear relationship. And more headaches present themselves when we use the linear probability function. These next two problems are rather technical, but important nonetheless. The error term expresses the difference between the actual dependent variable value and the predicted value. We assume that errors occur at random, and therefore the error term follows a normal distribution, that is, a distribution of probability that is shaped like a bell. To indicate the bell shape, we need to have many potential values for the error term. So let's go to the whiteboard for a second to see how this works. So here is a, a random error that has values following a normal distribution of probability. We have a lot of random terms that occur at the mean, and only a few random terms that are extremely small or extremely large. So the error term has an expected value of 0. Right here. That has only a few observations at the extreme value of 5 as well as at the extreme but negative value of -5. So we need a fair number of random errors to indicate the bell-shaped curve. However, in the linear probability function, there are not many potential values of the error. There are only two possible values given the value of the independent variable. So here is a general example. For example, we could be looking at a sloping function where y was equal to 1 if we found that sloped and otherwise was equal to 0. Okay, uh, the predicted probability of sloping predicted by the model was the intercept A plus B times the number of years of imputation for respondent I. So this was the case in which the actual respondent was indeed smoking. The only, the only possible error in alternative is that the respondent did not smoke, but the predicted probability of smoking again is A plus D times the number of years of education for that particular respondent. Now, the residual is the difference between the actual value of y and the predicted value. In this case, there are only two possible values for the residual. One minus the predicted value, or 0 minus the predicted value. And that's it. We don't have this rich distribution of potential errors that we had when we were looking at the whiteboard. But a distribution of a random variable that has only two values cannot possibly be a normal probability distribution. That is, it cannot indicate a dot-shaped curve for all of the divisibles that are possible. Here is a slightly more technical problem. In all of this, we assume that the error terms do not depend on the explanatory variables. The whole philosophy behind all of this is to distinguish between systematic factors that may affect the dependent variable and unsystematic factors. For example, education is a systematic factor in terms of smoking because it has a very stable impact on the probability of smoking. More education will lower the chances of smoking. Anything that is not systematic or predictable in that sense belongs in the error term. So here's why the dependent variable that we wish to explain. And then a plus bx is just a systematic impact on y. And then anything else is by definition not systematic and therefore may occur at random. So here is the predicted value of a model a plus bx, which is systematic, and then anything else is unsystematic, unpredictable, and thus therefore into the error term. This clear distinction between independent variables and random anticipated terms is at the heart of the whole approach to OLS. So, in short, the error terms are independent of the x variable, the independent variables. This is true for all characteristics of the error terms. They are all independent of x. In particular, the variance at the end of time does not depend on the independent variables. So you remember that variance is a measure of dispersion of a variable. The more the scattered, the more dispersed that variable, the greater its variance. So let's look at an example. Again, at the whiteboard. So in particular, variance is the sum of the square of deviations of the variable from its mean. Although denote values of x with the subscript I, and then here is the mean of x denoted with the subscript m, and then we will square each of those deviations and add up the squares. So here is a numerical example. Suppose that x has 1, 2, or 3 values. And the first value, to make it simple, is 1. The second value is 2. And the third value is 3. So the mean in this case for this distribution is 1 plus 2 plus 3 adding up to 6 divided by the number of observations. There are 3 observations, and so the mean value is equal to 2, or 6 divided by 3. All right, so for the first observation, we have 1, the value of that observation, minus 2 squared. So the second observation, the actual value is 2, equal to the mean for the distribution. And then for the third observation, 3 minus 2 also squared. So the sum of the square deviations in this case is from the first observation minus 1 squared plus 0, which is also squared and 1 to the power squared, total of 2. So the sum is 1 plus 0 plus 1 equal to 2. And then to express this as a variance, the sum of the squared deviations divide that sum by the number of observations. I assume that this is not the sample, but a statistical population that just consists of 3 observations. So 2 divided by 3 gives us the variance of this distribution. It is 2/3. The important thing to note I will bring up the definition now more fully over here. The critical point to note is that variance will increase as the deviations become larger and larger. Remember that the deviation is the difference between the current value of x and the mean value of x across all the observations. Okay, so in short, the variance of the error term reflects the amount of dispersion and potential values of the error. We assume that the error term has one given variance that does not uh, depend at all on the independent variable. So, for example, from the whiteboard, consider a model that relates consumption to income. Here is the well-known tangent function. The amount consumed by a household depends positively on its income. If this model is detecting all systematic effects on consumption, that is, if only income has a systematic impact on consumption, then any difference between actual consumption and the predicted consumption on this right-hand side, any of those differences occurs as a random variable. So in this graph, let's put income on the horizontal axis across all households. And then we will assume that the variance of the average term is always the same for every level of income. Remember that the average term is expressing the difference between the actual value of consumption for a given household and the predicted value for that household. So I will note that over here, the error is the difference between actual consumption for household I minus predicted consumption for that household. So this is the value of the average term that occurs for household I in a data set. Across all households, the variance of the average is always assumed to be the same regardless of household income. So, for example, for a low level of income, here is one potential level of consumption. Here is another potential level, and we assume that at a high level of consumption, we have a dispersion of values of similar size. So let me clear away this graph so that we're no longer looking explicitly at the variance of the income on the vertical axis, but instead of measuring consumption for each household. Here is uh, the value of consumption predicted by the regression line. So this is a bit different from the earlier graph. The population just refers to all households. Okay, for any particular income, we may have several possibilities for consumption. For example, at, at this level of income, let's say $10,000, we may observe a high value that of consumption or a low value right here. Those are possible outcomes given an income, let's say $10,000 per year. And then here is a possibility for high income maybe Donald Trumps. So of a probit $10 billion. In this case, of course, the expected consumption will be higher for the billionaire than it had been for the pauper. However, we are interested at the moment not in the level of consumption, but the dispersion in possible consumption values. So here is one possible level of consumption for the billionaire, and here is another. Although these levels of consumption are higher than for the pauper, the dispersion of those values is about the same in either case. That is the assumption that all of us makes, that the dispersion of consumption is independent. Dispersion of the return, I should say, is independent of the level of income. So the errors that occur here in terms of regression line are about the same as the errors over here. So if we have if the variance, the errors is constant, with respect to the independent variables, in this case income, then the errors are said to be homoscedastic. However, you may object that this assumption of a constant variance of error terms is not realistic. For example, that the poor household may have fewer opportunities to consume than the rich household. So, for example, here again is our population regression line. Now, for the low-income household, there are not many savings, so the household has to consume very close to its level of income. So here is one possibility. Another one right here. Both possible levels of consumption are very close to the regression line. So the error term, that is the difference between actual consumption and the predicted consumption, or on the regression line, those errors are very small. But now, back to Trump's case, Trump may be able to borrow easily, so he can consume about his annual income. This one possibility, or if he chooses, he can tighten his belt and consume at a much lower level. But there is greater dispersion in consumption values for the billionaire than for the pauper, meaning more opportunities to vary consumption for the billionaire. And therefore, the difference between actual consumption and predicted consumption is larger for the billionaire than for the pauper. In the case of the variance of the return, given income is larger for higher levels of income. That is, the variance of the average is not constant with respect to income. The variance is increasing at higher and higher levels of income. This is not homoscedasticity. So I will note that case over here. We will call this dependence of the variance of errors on the independent variable heteroscedasticity. Okay, so it is fair to ask why did this very technical detail make a difference to our results? The reason is simple. All of us assumed homoscedasticity, that it assumes independence of the error variance from the independent or X variables. In particular, it assumes constant variance of the error when it calculates the standard error of the coefficient estimate. One way of understanding this is to think about, again, the consumption function. In in the population, the statistical population of all households, the coefficient B is a constant. However, when we take samples of households, the value of B may vary from one sample to another. The standard error of that estimate reflects those differences that dispersion in the sample coefficient estimates. So, for instance, here's one sample of consumption and income across 15,000 households. And we find for those households that an estimate of the coefficient of income is equal to 3. Now, here is another sample, different intercept, and a different coefficient of income. To oversimplify for a moment, the standard error of the coefficient estimate reflects the change from 0.3 to 0.4 in our estimates of the income coefficient. The standard error is important because it determines a key statistic. You remember that we use T to indicate the likelihood that a sample value is not zero. If it is in the null hypothesis for the population. So the t-value is the coefficient estimate divided by the standard error of that estimate. If we have heteroscedasticity, then we will make a mistake in our calculation of that standard error. And therefore, we will distort our values of t. They are no longer useful to determining whether we have statistical significance or not. Heteroscedasticity will distort the denominator of the p-value, and for that matter, will in general invalidate inferential statistics. So there is the problem. In short, dependence of the error on the independent variable will make life difficult for us because we can no longer test for statistical significance. So you remember that statistical significance is just the idea that the coefficient in reality may not equal zero. So there is the problem to consider. Hypnoscedasticity. And it turns out that in the linear probability function, hypnoscedasticity is almost impossible to avoid. And here is why. Let's look at a sample regression line. So this is our estimate from the sample, for example, of consumption and income. With the linear probability function, the dependent variable y is always either 0 or 1. So for example, in a smoking model, we have for an observation 1 if it is from the smoke and 0 otherwise. So all the dependent variable values are occurring either on this line or this line over here. Now, let's say that the blue dots represent our actual values of the dependent variable. We have 6 observations here. And we estimate the blue regression line. Good. When x is high, our values on the regression line are close to the actual values of the dependent variable. So here is our predicted value. So here is our predicted value given that value of x, and here is the actual value. The difference is very small, and so the errors are small as well. Now look at the other extreme for the regression line. Again, given the value of x, there is very little difference between the actual value of y and the predicted value. The errors are very small. So the variance of the error is small over here at this extreme, and it is small over here At the other extreme, we have a small variance of the error for large and small values of x. Now, consider a medium value of x right here. Now, this is our predicted or prediction for y, but remember that y in reality is either 1 or 0. So in this case, we have large errors, large differences between the actual and the predicted values. The base of the error term is larger for medium values of x than it is for large or small values of x. That is to say, the error variance is not independent of the level of x. That is helpful scarcity. And that is a summary of our discussion so far. And a continuation of our summary. I should say for moderate values of x. Moderate rather than high. Again, heteroscedasticity will display our standard error of the coefficient estimate and therefore invalidate the t-statistic since t is using our estimate of that standard error. You remember that the standard error is the square root of the variance for the sample means. A reminder of the t-statistic. So, in short, the linear probability function is simple, easy to understand, and still useful from time to time. But we still confront such problems as unrealistic predictions for the function and also uh, violations of the assumptions that underlie OLS, especially normality in the error term and homoscedasticity, this independence between the independent variable and the variance of the error term. Since our computers these days are so powerful, we will no longer have to settle for the linear probability function. We can now uh, estimate functions that will be satisfactory, especially on the balance on the dependent variable. We do this by modeling explicitly particular probability distributions, logistic and the normal. So I will stop there for tonight, and then later on we will look in more detail at the logit distribution. Thank you. That's it.